Show that 1 over log to the base a of b equals log to the base b of a, where a and b are greater than 0 and both a and b are not equal to 1. What we can do here is change log to the base a of b to a log term that's in base b. So how do we do that? Well, we want our new base to be base b because the log term on the right hand side is in base b. So b is our new base, so we get log to the base b of this argument here, and we divide by log to the base b of our old base, which is a. So that's how we change base. So base b can be any new base, but we choose base b because that's the term on the right hand side. Now, what is log to the base b of b? Well, that's just 1, because b to the power of 1 is itself. Notice here that both a and b are greater than 0. Why is that mentioned? Well, that's just stating that the argument of the log function has to be positive. Well, if the base is positive, so if a is positive, then b has to be positive, because we can't get a log to a positive base of a positive number. Of a negative number. We can only get the log to a positive base of a positive number. So we need both a and b to be positive in order to be able to calculate log to the base a of b and log to the base b of a. We were also given that a and b are not equal to 1. Now, why is that given? Well, if both a and b are 1, then this equation is trivially satisfied, because we have 1 divided by log to the base 1 of 1. If we put 1 in for a and 1 in for b, well, log to the base 1 of 1 is 1, because 1 to the power of 1 is 1. So that's equal to 1, and the right hand side, log to the base b of a, is just going to be log to the base 1 of 1 again, which is 1. So that's a trivial satisfying of this equation. In part 2, we want to show that 1 over log to the base 2 of c plus 1 over log to the base 3 of c plus 1 over log to the base 4 of c, etc., as far as 1 over log to the base r of c is 1 over log to the base r factorial of c, where c is positive and c is not equal to 1. Well, c has to be positive because c is the argument of a log function whose base is positive, and we can only get the log to a positive base of a positive number, so c must be positive. C cannot equal 1. Why is that? Well, if we try to calculate log to the base 2 of 1, say, if we try to for this first term here, we get 0, because 2 to the power of 0 is 1. But then the first term is going to be 1 over 0, and we cannot divide by 0. So these denominators cannot be 0. They will be 0 if c is 1. So c cannot equal 1, basically, if we don't want division by 0. Now, let's just use the previous result. We can write 1 over log to the base 2 of c as log to the base c of 2. See, we just interchange the base and the argument. That's what we learned from part 1. That 1 over log to the base a of b is log to the base b of a. So we just interchange the base and argument. Interchange a with b. So I've just done it here for this one. 1 over log to the base 2 of c is log to the base c of 2. And we can do it for all of the terms in the series. So now, summing the series on the left hand side, summing all of these terms, is just the same as summing these terms here. So now, this is what our left hand side becomes. And since all the bases are the same, they're all equal to c, and we're adding log terms, and all the log terms just have 1s in front of them. 1 times log to the base c of 2 plus 1 times log to the base 3 of c, etc., as far as 1 times log to the base c of r. We can use a rule for combining all of these into a single term. That rule tells us that we can write all of this as log to the base c of the product of all the arguments. That is 2 times 3 times 4 would be the next one if I had it written down, times 5, all the way up as far as r. We multiply all the arguments together. So we're just using this rule here that I proved in an earlier video, where the bases are the same and we're adding the log terms, we just multiply m by n. We can imagine extending this rule to more than 2 log terms, as we have here. We just multiply all the arguments together as far as r. But 2 times 3 times 4 as far as r is just r factorial. Now what we can do is use what we proved from part 1 in reverse. See, if we have log to the base b of a, we can write it as 1 over log to the base a of b. So if we have log to the base c of r factorial, we can write it as 1 over log to the base r factorial of c. R factorial is just a number. And that's what we had to prove. Given two real numbers a and b, where a is greater than 1 and b is greater than 1, prove that 1 over log to the base b of a plus 1 over log to the base a of b is greater than or equal to 2. Now, first of all, I just want to mention why a and b have to be greater than 1. Let's suppose that a is equal to 1. Well then, if we look at this term here, we will have 1 over log to the base b of 1, which is 1 divided by 0, because b to the power of 0 is 1. Log to the base b of 1 is 0, and that's undefined, so we can't have a equal to 1. Similarly, we can't have b equal to 1, because in the second term, if b is equal to 1, we have 1 over log to the base a of 1, and log to the base a of 1 is 0, and we can't have division by 0. So b can't equal 1 either. We're given some further information, that is a is greater than 1 and b is greater than 1. So it appears that a can't lie between 0 and 1 either. A and b can certainly not be negative, because we cannot get the log of a negative number if the base is positive. Now we saw in the last question that we can write 1 over log to the base b of a as log to the base a of b. So we can change this term here so that it has the same base as the second term. In other words, so that it has base a. So we can replace this here with log to the base a of b. Now if you didn't see the last question, which is in this video, then I can show you why this is true again. We change this term from base a to base b. So we want our new base to be base b. So we get log to the base b of the argument, which is b, and divide by log to the base b of our old base, which is a. But log to the base b of b is just 1. So we see that log to the base a of b is 1 over log to the base b of a. We just interchange these and take a reciprocal, and then these are equal. So now we can rewrite the left hand side here as log to the base a of b plus 1 over log to the base a of b. So both log terms have the same base, and we want to show that it's greater than or equal to 2. So we just write it down first and deduce some consequences until we get something that's obviously true. Now, just to simplify or make the algebra easier to write down, I'm going to let x equal log to the base a of b. So we'll have x plus 1 over x greater than or equal to 2. This is what we have to prove. If log to the base a of b equals x, it means that a to the power of x equals b. Now we're given that a is greater than 1 and b is greater than 1. So if both a and b are greater than 1, that actually means that x must be greater than 0. Because if x equals 0, we would have a to the power of 0 equals b, but a to the power of 0 is 1, we would have b equals 1, which contradicts the fact that we're saying b is greater than 1. So x can't equal 0. Now, the way to see that x cannot be less than 0 is to consider what happens if x is less than 0. Okay, so I'm saying here that x has to be greater than 0. We've already shown that x is not equal to 0. But let's see what happens if x was actually less than 0. If x was less than 0, then x would equal minus k, where k is some positive number. That would mean that a to the power of x would equal a to the power of minus k, where k is some positive number. See, x is now, we're saying, just imagine x is negative. Well, a to the power of minus k is 1 over a to the power of plus k. Now, a to the power of plus k is greater than 1. Why is that? Well, the reason is because a itself is greater than 1. So we were given at the start that both a and b are greater than 1. Now, if you take any number that's greater than 1 and raise it to a positive number, so k is a positive number, you will get a number that's greater than 1. So what will happen here is we will have 1 divided by a number that's greater than 1. So we end up getting a number so this number here is actually less than 1. If the denominator is greater than 1, then 1 over this will be less than 1. And since we're saying that a to the power of x equals b, and we also want b to be greater than 1, that's what we were given, that we're given that b is greater than 1, then we get a contradiction. So a to the power of x equals b, and we find that b is less than 1. So there's our contradiction. We can't have that. So we can't have x less than 0. So x must be greater than 0. So if we assume that x is less than 0, we contradict the fact that both a and b have to be greater than 1. So now that we've established that x is greater than 0 and strictly greater than 0 can't equal 0, we can handle this inequality. We can multiply both sides by x without worrying about the direction of this inequality. If we multiply both sides by x, we get x squared plus 1 is greater than or equal to 2x. With any inequality, you should try to get 0 on one side. So we get x squared minus 2x plus 1 greater than or equal to 0. And hopefully this thing here is a square, and it is. We can actually factorize this as x minus 1 squared. And any expression squared is greater than or equal to 0. So this is definitely true. So we can then just reverse all our steps, and we have now proven this here. Under what condition is 1 over log to the base b of a plus 1 over log to the base a of b equal to 2? So that's the equality part of our inequality, which I didn't show. We got down to this inequality here, which we know is true, because any quantity squared is greater than or equal to 0. But what's the condition for x minus 1 squared to equal 0? Well, that condition is that x must equal 1. If x equals 1, then we have 1 minus 1 squared is definitely equal to 0. X, remember, is log to the base a of b. So we want log to the base a of b to equal 1, which means that a to the power of 1 equals b, or a equals b. So that's the condition for equality, for x minus 1 squared to equal 0. And then we can reverse all the steps, as you saw from part 1, and conclude that 1 over log to the base b of a plus 1 over log to the base a of b equals 2. And that's quite easy to see if we just look at this thing here. And imagine putting a equal to b. So you would have 1 over log to the base b of b, say you put a equal to b, plus 1 over log to the base b of b. Well, that's just 1 over 1 plus 1 over 1, because log to the base b of b is 1. So we have 1 over 1 plus 1 over 1, which is 2.